projector started, and we'll go over a few of these announcements. They're nothing too major. I did get your paper that I found slid under the door. I haven't had a chance to go back through it yet.
I didn't rewrite it. That paragraph because I thought about start adding another thing. That's rewriting the paper.
Yeah.
That's a breach of protocol. So.
Right. No, I understand. Yeah.
Okay.
Perfectly fine. Today, things are going to be crazy for a little bit, as if they aren't normally crazy, but I've got to get today in my final grades for the first mini-term. And I worked on them this weekend and worked on them this morning. But it's almost like the first of the terms all over again. There are people wandering the hall, not knowing where their classes are, or not knowing where in fact, some instructors wandering the hall from the other campus trying to find classes on this campus. It was just sort of nuts. So part of the day in unlocking doors for people and getting things done. So anyway, I've got to finish getting those grades in. They're all but putting them in the right place. So I've got them all calculated and stuff, but just getting them in the right form. So that's going to be the number one part. I've got to have it done today. And then something that was due last Friday I couldn't get to. I've gotten it mostly done, but I've just got to get the final touches on student learning outcomes. They were due last Friday, and just the end of the week, I could not get them done. And then by the end of the month, we have our, whatever they call them, the course for all the majors. And I've got some time on that. So, and then on Wednesday of this week, midterm progress reports. Well, I've got plenty from you. I've got your paper, which had a good score, and I'll revise that, but that'll be fine.
Let's leave it alone.
Yeah, okay. It's not going to get much better than that, but it could get another point or something like that. But anyway, there's a lot of things piling up right now, so I'll try to get that done. Our volleyball team has a match tomorrow evening versus Southern Union Community College. The trouble is it's down in Wadley, Alabama, and I'm not about to go down there. It's at 6 o'clock. So if you happen to be driving by Wadley around 6 o'clock tomorrow evening, stop in and cheer the team home to victory. Okay, that's all over with. I need to take that down and have it shredded. The NASA's Community College Aerospace Scholars Program is receiving applications through Wednesday, day after tomorrow, October 16th. So if you or anyone you know may need that information, please tell them it's here. I'll be glad to share it with them. Okay, so let's pick up from the current slide. And we're in Chapter 13, Functions of Several Variables, and we're in 13.3, which is partial derivatives. And we've done example 1, 2, 3, and 4, but example 5 is not in the PowerPoint, so that's what we're doing. I think, actually, there's more white space there than here, so let's go there and do our example 5. Let me get my... Yeah, before we do.
When they say, talk about the area of a parallelogram,
Right.
isn't it the same that if the parallelogram is moving, wouldn't it be the same as the plane moving? Would it be the same thing?
Okay.
The plane.
The,
you got a parallelogram sitting here.
Yeah.
I'm taking it as it's a smooth surface.
Right.
Well, wouldn't that be the same as if they say is the plane
Right.
of that parallelogram?
Right.
Is that the same thing? If the plane, if the parallelogram is moving,
Right.
the rate of change
Right.
would be the same as the parallelogram or the plane would be the same, the rate of change.
Yeah, I would think so. What is this in reference to? A test question?
No, that's in reference to 5.
Oh, example 5, which you're about to start.
Yeah.
Oh, okay, right, okay. That's why I was trying to, I said, I can't remember this one, something that we'd already done. Okay, got you. Let's see, let me read it and see exactly what it's talking about. Using partial derivatives to find rates of change. The area of a parallelogram with adjacent sides A and B, okay, and the included angle theta is indicated by AB sine theta, as shown in the figure here. And let's just get that down. Now, mine's not going to be a parallelogram, but I'll do the best I can on that. This will be side A. This will be side B. This will be opposite side B and opposite side A. Now, let's just suppose that this is a parallelogram AB, the two sides of it, and this is the included angle theta. Now, they say the area of that parallelogram with those two adjacent sides and the included angle is given by AB sine theta. Now, how do we get that? Well, they show a little indication here by dropping the perpendicular from the point up there and extending the base to there. Now, parallelogram, this angle and that angle are the same, right? Those two thetas are the same because they're parallel sides, so the angles would be the same. And this would be side A also, okay? Well, they say the area here is AB times the sine of theta. AB times the sine of theta. Okay, now, how do they get that? Well, number one, let's see, what if we drop the parallel perpendicular line there? This triangle is exactly that triangle. Okay, exactly. So the area of this parallelogram is the same as the area of that rectangle. And that rectangle is, and by the way, this length is exactly that length, of course. So the length here will be side B. Well, that is side B up here. So yeah, that was obvious. That and this will be, this height here is, the sine of the angle theta is opposite over adjacent. So this height here will be A times the sine of theta. So B times A sine theta, that's going to be the area of the rectangle and the parallelogram. Okay? Now, maybe I didn't need to go through all that, but just to see. Now it says, find the rate of change of the area with respect to little a, for A is equal to 10, B is equal to 20, and theta equal to pi 6. Okay? So this is going to be pi 6. This is going to be pi 6. I don't need them both. I'll write them down. A is 10. And B is 20. Now, obviously, mine's not to scale. Very obviously. Now, what do they mean, and this may be what you're asking, find the rate of change of the area with respect to A. So what if you allow A to lengthen or shorten? Okay? How does that affect our overall area? Well, what we're doing then is doing dA, d little a. You know, how does A change with that? The only trouble is we got more than one variable, so these need to be, what were they called? Crooked D's or slant D?
Crooked D.
Crooked D. Huh?
Curly D.
Curly D. Curly D. Curly DA, curly DA. Okay. That would be, what would that be?
As it stands now, A, B, cosine theta.
Okay, now the theta doesn't change. It's constant. And the B doesn't change. You're only changing A. So that would be little a. The capital A is changing with little a. As little a is lengthening or shortening, how is capital A changing? That's what the rate of change of A with respect to A would be. The B and theta are treated as constants. So that would be what? B sine theta, exactly. Okay? So, what is the rate of change there? 20. And what's the sine of pi 6? 1/2. So that would be 10. And that would be area units per length unit, so that would be length unit. And they don't give a unit there, so centimeters, meters, yards, furlongs, whatever it happens to be. That would be the rate of change there. Okay? Now the B part, this is A part. The B part would be what's the rate of change of the area with respect to theta. This time we're letting the theta go from pi 6, increase or decrease. Okay? So what we're doing then is curly D, A, curly D, theta. Okay, and that's what you started giving me a minute ago, I think. What would that be? In this case, we're leaving A and B, little a and little b, constant. We're varying theta. So what would that be? That would be AB cosine theta. Is that what your question was?
Yeah. Well, see, at first we had you said the change of area.
Right. Okay.
But now I'm looking at that area as it stands now.
Right. Okay.
Now we're going to change the angle.
The angle. So, but leaving the B20 and the A10, and let this swing like this. That would be increasing theta, this would be decreasing theta. Now, pi 6 is much smaller than that, but just in general, that would be doing that. How does that change the area here? Well, as it changes, as this gets larger, now you have less of this sharp angle here. You're moving more toward a rectangle. So, and this is getting taller. The B isn't changing any, but it's getting taller, so your this theta is increasing, and sine is increasing, so that would be increasing your area. And of course, a decreasing theta would be making that get smaller. Now, I'm sure there's a limit how much you can increase it, and it still be a parallelogram. I would think almost 90. I'm wondering if you can flip it back this way. It seems like that would get into some real big problems. So I think we just limit this to up to 90, but that's would be increasing areas, the theta's getting bigger, decreasing areas getting smaller. The area that's in there with B, A and B staying the same lengths. Is that what you're...
No, I'm trying to see if this area you're talking about, this...
The area inside here.
Yeah.
Yeah.
Can we consider that whole figure a plane?
Yeah.
Can we?
Okay. Yeah, this planar region right in here.
Yeah, that region.
Right.
If we do the change of A with respect to the angle, does that region stay the same or does it change?
No, it changes because let's go to something.
The angle up there is changing, so that's going to make the area larger.
Yes, it's larger as the angle gets larger, smaller as the angle gets smaller. Because you see, ultimately, if the angle went to 0, you got no area at all. And if it goes to 90 degrees, then you have a rectangle of area AB, and that's going to be bigger than this one would be because these angles there, AB sine, or A sine theta is less than A. Right. That's the hypotenuse. So A sine theta is less than A, so that part grows when the theta increases, and see the A moves further up because now it's straight up. It isn't growing any, but that length is moving up here, so that will be increasing the area up to 90 degrees. Yeah. And decreasing down to 0. So what would that be? Partial of A with respect to theta. AB cosine theta, where little a is 10, little b is 20, and cosine theta is second. No, yeah, you're right. It's pi over 6. The theta is pi over 6. What's cosine of pi over 6? Square root of 3 over 2. Okay, so that would then be 100 root 3. Okay. Which is a pretty large rate of change, especially since the rate of change of the other is pretty small, 10. The rate of change as you change your angle is increasing fairly dramatically, 100 root 3. That was more than 10 times the increase of rate of change than what it was just increasing your length. Okay. Nothing dramatic about this. The thing is just letting you see that you can keep all the other constants through and just change one of the variables. And that's what a partial derivative does for you. It tells you that without having to do too much messy analytics, just let it do the work for you. Is that what makes sense? Yeah. Okay. Now, I think now we go to a new slide, which is partial derivatives of a function of 3 or more variables. The only problem here is they're going to be really hard to picture, okay? You just have to, you can picture up to 3 dimensions. That 4th dimension, though, gets pretty difficult to do. The concept of a partial derivative can be extended naturally to functions of 3 or even more variables. For instance, if w is some function of x, y, and z, then there are 3 partial derivatives, each of which is formed by holding the other 2 of the variables constants. Okay? That is, to define the partial derivative of w with respect to x, consider the y and the z to be constant. Just like we did in that last problem. You had a, b, and theta. That was 3 variables, and you're looking at the area, which is the 4th variable. So we just did this, okay? That is to define, okay. A similar process is used to find the derivatives of w with respect to y and then with respect to z. We did 2 of those with respect to a and with respect to theta. We could have done it with respect to b in the previous example, and we'd have had exactly this, okay? And here's how they're defined. The partial of w with respect to x. Another way to write this is f sub x of x, y, and z. That's the limit. Now notice you're only letting the x change here. F of x plus delta x, y, z minus f of x, y, z. The y, z's haven't changed. They are constants. And you're just doing the change of f of x, of the x variable with respect to x. So that's why this f of x. And then when you do it with respect to y, you let the y, and only the y changes. X stays the same, the z stays the same, but the y goes from y plus delta y minus y, f of y, divided by delta y. Okay? And partial with respect to z, same type deal. Let the x and the y stay the same, and the f of xy, z plus delta z minus f of z, divided by delta z. In general, if w is equal to f of x of 1, x of 2, x of 3, x of 4, up, all the way up to x of n, then they're n partial derivatives. The partial of w with respect to x sub k, and this is just for k to one of those n. F sub x of k would be x of 1, x of 2, of every one of those. You just take the partial with respect to that one variable, leaving all the rest of them constant. For k then counts from 1 to n, so you can do it. Partial of w with respect to x of 1, the first variable, partial of w with respect to x of 2, the second, and all the way up to that. So you get k first partial derivative separately. I mean, n first partial derivative separately. Find the partial derivative with respect to one of the variables, hold all the other variables constants, differentiate with respect to that given variable, and that one only. Okay. Oh. So here's example 6, top of page 898. To find the partial derivative of f of xyz, which is xy plus yz squared plus xz with respect to z, consider x and y to be constant, and then just do this. Why do they do it for you? Okay. Let's just do it. We've taken the partial with respect to z. What would that be?
xy0 being that 2yz.
2yz.
And then just x.
Plus x. That's it. 2yz plus x. Perfect. Okay. Are they going to do it for you here too? I'm afraid so. Okay. To find the partial derivative of f of xyz equal to z sine of xy squared plus 2z. Yeah. Okay.
Now,
With, yeah.
we got to be positive, I think. So
What's that?
we got to do d of z out here. It's like a product. It's a product, isn't it?
Yeah. Oh, you mean of this one here or
Yeah.
this one here?
No, the one we talked about now, b.
This one, the b one. Yeah. Yeah, you're absolutely right. To find the partial with respect to z, this is a product rule. You do this one, holding that constant. I mean, the partial of this times this, plus this times the partial of this.
Yeah.
Well, the partial of this is going to be a chain rule, that, you know, so there's all sorts of things. So in that first piece there, I guess I can't cover it. I'd be blocking your view if I did. So let's do it.
Hold z constant.
No.
And,
Oh, wait, yeah.
and
Well,
then
do
you
the-
go, and then you're going to differentiate the sine xy plus.
Right. Okay. So that's what they've done here. Z constant, not z constant. Z, the function z times the partial of this one.
Yeah.
What is the partial of this one?
It's going to be with respect to z, that's the sine of.
No. Partial of that with respect to z.
That's going to be z times the derivative of
Right.
that thing inside. So we're holding
Okay.
x and y constant. So sine x and y goes to 0. Then we just got 2.
Okay. But it's, okay. Remember, if you're taking
Oh, that's
derivative.
right. Derivative of the whole thing, the product.
Yeah, yeah. Okay. The z times derivative of this, we'll start with the outer function. Derivative of sine is cosine of this thing here. Then chain rule is just in the 2. So the 2 will be there. So that gives you z. Well, they're going to get to that in the next step. Okay, but yeah, z times this derivative plus this thing, this is the product rule, times derivative of that, which is just going to be 1. So we can do this one. They did the first step for us, but this is a multi-step. So this will be z, that just comes down, and then we just said what this would be.
Z Z times the sine of
Not
cosine.
Cosine of
X, y squared plus 2.
2z. The whole thing.
Whole thing, that's right.
And then take the derivative of the inner part. That's the chain rule part. And that would be 2. Okay, so there's your first term of it. Plus,
The sine of that whole quantity
yeah,
is times 1.
times 1. So I won't even bother to write that down. Okay? So that's what the answer is. Okay? And they just flash it up there. And let's see how close we got. Oh, they're going to take, yeah, it comes out exactly the same, except they put the 2 on the outside here, the z on the outside there. Sure, on the next step, they'll pull them together and make it 2z cosine xy squared plus 2z. Oh, he did decide to show up today. Huh? Okay. Good to have you here. Josh is here. All right. We're in chapter 13 still, functions of several variables, and 13.3 partial derivatives. We're at the doing, where are we doing it? Oh, okay, yeah. Example 6 at the top of page 898. We've just done the A one, and we just finished the B one on page, example 6 on 898. We're getting ready to do C. Any questions before we proceed to C? Unfortunately, the book does the first step for us, which sort of aggravates me, but I'll try to hide it if I can. So, oh goodness, I think we showed everything here. To find the partial derivative of this one, f of x, y, z, and w, which is x plus y plus z divided by w. With respect to w, we count the x, y, and z as if they're constants, and then here's what they do. What is the partial of that with respect to w?
Okay, we just move W, take that minus 1, that's just like 1
Yep.
over x, and you're going to square the W and leave the constant the same.
Right?
So we just have x, y plus z over W squared.
Yeah, with the minus in front of
The minus.
Yeah, okay. Yeah, minus x plus y plus z over w squared. Perfect. Exactly the same. Okay. Now, I like the way you did it too. Just, I would put parentheses around this and just think of that as a constant times w to the minus 1. Take the derivative of that would be minus 1 times this thing times w to the minus 2, which should put back down over w squared. Perfect. Okay. Now, we've taken first partials, and they were fun, weren't they? Glorious fun, okay? But how about taking higher order partial derivatives? Not meaning higher dimensions, but actually higher order partials, okay? And this is where things get a little more interesting, okay? If you have this, let's go back to 2 independent variables, 1 dependent variable. If the function z is equal to f of x, y, has the following second partial derivatives. Now, if your first time you take the partial of that f with respect to x, you get f sub x, or d, curly d f over curly d x, okay? But the second partial with respect to x again is, if you'll notice this, curly d with respect to curly dx of curly df with respect to curly df. You get 2 curly d's next to each other, just like a second derivative, only these are partials, with respect to x squared. Now that's an odd notation, but it's the curly dx times curly dx is curly dx squared. It's not curly d of x squared, just like it wasn't before, okay? Now, in our shorthand notation, which I prefer, is f sub xx. It's just so much easier to write than lots of curly d's, okay? And if we did the same thing twice with respect to y, then you get curly d by curly dy of curly df by curly dy, and that's 2 curly d's of f over curly dy twice, or squared, and that's f sub yy. Okay, those are fine. But you see, you don't have to do them the same. You could take the differentiate first with respect to x and then with respect to y. And that, now here's where it gets a little trickier. This is very straightforward. You first take the partial of f with respect to x, curly df by curly dy. Okay? Then you take the curly d of this thing with respect to y, and that gives you 2 curly d's f and curly dy, curly dx per curly dx. Okay? It's written that way. But if you think about it the other way, this thing would be f sub x. That's the first partial you did. And then you take the next one with respect to y, so that one goes to the right. This, the sort of like the Leibniz notation, it goes to the left, the subscript goes to the right. This is saying you first take the partial with respect to x, which we did here, and then the partial of that with respect to y, which is exactly what that's saying, but written the other way, the partial with respect to x goes to the right, and with respect to y is to the left. So you just have to keep in mind that these two are reversed, depending on your notation. Now, you want the good news? It doesn't matter.
Yeah, I don't think it matters.
It doesn't matter. Well, with some conditions on it. And most of the time, those conditions are met. Okay, the fourth one would be first take the partial with respect to y, and then the partial with respect to x. So that's curly d by curly dx of curly df per curly dy, and that would be 2 curly d's f, and then curly dx, curly dy. But then written the subscript way, because you first took the partial with respect to y, the y is right next to the f here, and then you took the partial of that entity, the the f sub y with respect to x. That was the second thing you did. That puts it to the right. Here it's to the left, here it's to the right. The third and fourth cases are called mixed partial derivatives. Okay? And with just a little caveat, you'll see that everything is fine. But let's first do this, okay? Find the second partial derivatives of f of xy is equal to 3x squared minus 2y plus 5x squared y squared. And then we're going to figure out what they are. So they want all the second partial derivatives. So what you reckon we need to do first? Really doesn't matter too much, but at some point you need to do what? Yeah, let's take the partial with respect to x first, and what would that be? 3y squared.
6xy.
No, wait. If you're doing with respect to x. Doing with respect to x. Oh, yeah, you leave them out. Okay. And what's the second part? Plus 10x y squared. Perfect. Let's go on and do our other first partial. We only have two. F sub y would then be, this is what you're wanting to do, 6xy minus 2 and plus what?
10x squared y.
Oh, 10x squared y. Okay, I thought you said 12. My hearing is bad. That's perfect. Okay? Now, said find the second partial derivatives. Which one you want to do first? F sub xx? Okay. And that would be what? 10y squared. Done. What one you want to do next? Okay. Why did I write that? I don't know. Whoops. That's not what I wanted. That is what I want. Okay. There. Now, f sub yy would be 6x plus 10x squared. Perfect. Okay. Now, we still got two more second partials to do. Which one you want to do next? We've already done xx. Did you say xx?
No, I didn't. Oh, we got to do
X with respect to Y.
Right. Okay. So you want to do f sub xy, which will be using f sub x, but taking with respect to y. What would that be?
21.
Second?
21.
Okay. How about the first term?
6y.
6y plus 20xy. Okay. And then let's do our f sub yx. Okay, that's the last one we'd have to do, second partial. That would be what? 6y
Plus 10x squared.
taking the partial of this one with respect to x. 20xy. And looky there. As we guessed, or maybe you knew, those are exactly the same. You got there a different way, but they do appear to be the same. Now, they ask one more thing. Let's do f sub xy evaluated at minus 1, 2. So, of course, which one would we use? The one just above us here, f sub xy, and that would be 12. What? Minus 40, which would be negative 28, which would also be f sub yx evaluated at negative 1, 2, because they're the same thing. Okay. Now, it said, notice in this example, that it, well, let me go on. This is how we did it. Let's see how they did it. Make sure we got everything the same. All right to erase? Okay. So let's see how they did. Begin by finding the first partial, first with respect to x and then with respect to y. That's exactly what we got. 3y squared plus 10xy. F sub y was 6xy minus 2 plus 10x squared y. Got it. Perfect. Okay. Now, let's see what order they did. They did each of those with respect to the same variable, x. So this one goes away, and this is 10y squared. And that's it. Did this one with respect to y, you get 6x plus 10x squared. Okay. No resemblance there at all, so to speak. Okay. Now let's do the mixed partials, f sub, and we don't have the others to look at, but we did it and got 6y plus 20xy for both of those. And indeed, that's correct. Now, was that just happenstance because they happened to pick the one that's going to work out that way? No. They all, well, here's the deal. Notice that, and maybe they say this. Oh, and then I forgot, at negative 1, 2, that mixed partial would be 12 minus 40, which is minus 28, which we did also. Okay, no, they didn't say it, but here's the caveat, and it's not a major one. If f is a function of f and y, of x and y, such that f of x, y, and f of y, f sub y, x are continuous on an open disk for R, then for every, as long as these two partials are continuous on an open disk R, then for every x, y, and R, the mixed partials are the same. So when you do that second partials, they've got to be continuous. And that's all that's required. Okay? They don't have to be smooth, they just got to be continuous. Okay? There can't be any gaps, holes, or anything like that on the open disk line. So for every x, y, and R, then that will be the case. So it doesn't seem like a very major condition you have to meet, but every now and then it'll sneak up and you'll wind up with something that doesn't fit it and your mixed partials won't be equal and you think you made a mistake, but no, you haven't met the requirements. Okay. So, and that theorem, this theorem right here, applies to a function of 3 or more variables as long as the second partial derivatives are continuous. The second partials are continuous. Okay. All right. So here's example 8. Show that f sub x z is equal to f sub z x, and then we'll do third partials, xzz, xzx, xzx, f sub xzz, f sub zxz, and f sub zzx are all equal. As long as you have exactly the same partials, not necessarily in the same order, but exactly the same partials. So let's do it to it, okay? What you reckon we're going to need to do first? Well, you first got to do a first partial. Which one you want to do first? F sub x, okay? And this is of x, y, and z. I'll write it down. I haven't been writing it because it's just such a pain, but we'll write it here. Okay, and what would that be? Y e to the x. I can do that one.
Very easy.
Plus what?
1 over z.
Second? That's a ln.
Yeah, 1 over z.
So ln z?
X,
1 over z.
We're taking this partial with respect to x, not with respect to z.
Oh.
So log z is a constant, log z is a constant. Okay? So that's just a constant times x, and the derivative of that is the constant, which is log z. Okay? Now, you can go either one of two directions here. What do you want to do next?
Do you need f sub y?
You will not need f sub y for the things they're asking for up there at all.
So f sub z again.
Okay, you'll need an f sub z, so let's do that one as well. F sub z is equal to
1 over x over z.
x over z. You got that one, okay? Because the first term has no z dependence at all, so that's a constant. Derivative of that is 0. That one, what you're wanting to do before, derivative of log z is 1 over z. The coefficient is x. So, perfect. Okay, what you want to do next?
Fzx or xz. This is the first one on that.
Okay, f sub xz. Is that the one? Okay, let's do that. F sub xz. And this is also, I didn't write the other one down, so I shouldn't do this one. I've already started the parentheses, I'll do it. And what would that be? 1 over Z. You're absolutely right. And that's all, folks. And what's the next one you want to do?
Sub ZX.
F sub ZX. Okay, and what would that be? 1 over Z. So we've done this one. We've shown those two are the same. Okay? Now, we've also got the first step of that one done, right? F sub XZ. So we've now got to do F sub XZZ. That's really snoozing there, isn't it? Okay. And what would that be? All right, if I write this as Z to the minus 1.
Yes, negative Z, 1 over Z squared.
Okay. Okay, negative 1 over Z squared. Okay. If you want to write it that way, that's perfectly fine. I'll bring the minus up where it needs to be. Okay. There's that one. All right, we got that done. Now let's do F sub ZX. So we would need to do F sub Z X Z. And what would that be?
1.
Well, no. You're taking the partial with respect to Z of the very thing you just did. That's the same thing.
I'm sorry.
Yeah. Okay. Because that's the same thing. Okay. F sub XZ, F sub X is this, and F sub XZ would be that. Well, F sub ZX is that same thing. So take the partial of that with respect to Z, just like you did here, and you would get 1 over Z squared. Obviously, you're doing the same thing. Okay. But we've got one more to go, and that was your F sub, and we haven't done the, so we've got this done, and we've proven that equality is the same, but we haven't done F sub ZZ, which we need to do before we can do F sub ZX. So let's do F sub ZZ. And what would that be? Negative X over Z squared. Perfect. And then we need to do F sub Z ZX. That's what this is. And what would that be? Perfect. We got that, and we've shown it's the same as that. So yes, all those are the same. Let's see. Are those all the possibilities? Here we had XZ, XZZ, ZXZ, and ZZX. I think that's all the possibilities, isn't it? I think so. F sub. Yeah, that's it. Okay. And they're all three. Okay. You've done it and you did it well. Okay. Oh my goodness gracious. That ended 1:13:3. Somehow I don't see all of, oh, there they are. Okay. Good deal. Okay. So that finished the section. Homework exercises here would include any of the odds, 5 through 9. They should all be at Calc Chat. Any of the odds, 11 through 39. There's a whole passel and a half of those. All those odds should be at Calc Chat. 13 should be at Calc View. Then either 41 or 43, they're both at Calc Chat. 41's at Calc View. Any of the odds, 45 through 51, they should all be at Calc Chat. 45's at Calc View. Either 53 or 55, they should both be at Calc Chat. 53's at Calc View. Any of the odds 57 to 61, they should all be at Calc Chat. 57's at Calc View. Any of the odds 63 to 67, they should all be at Calc Chat. Any of the odds 69 to 75, they should all be at Calc Chat. Goodness gracious, my eyes are stinging like crazy. It's hard to read these things. Then any of the odds 77 to 85, they should all be at Calc Chat. 79 is at Calc View. 87 and 89 should be at Calc Chat. 91 and or 93 should be at Calc Chat, where 93 should be at Calc View. 95 and 97 are at Calc Chat. And by the way, these are part of Laplace's equation. So since they mention it here, there would be another potential paper topic, hint, because you can either write on Laplace, how did he develop this equation, what is this equation used for, that kind of stuff. And by the way, since you weren't in here when I said it, you may not go back and listen to the tape, the video, this Wednesday is when I have to report midterm progress reports, so it'd be nice to have a score by then. So either research paper or the first test, either one. Or both. I'll take them both. Yeah. Okay. All right. Where did I leave off? That was Laplace's equation. Then there's the wave equation, another one that's used a lot in physics, either 99 or 101. You're not having to define the physical part of it, but that is the wave equation there. 103 is dealing with the heat equation. 105 is dealing with, I never know how to pronounce his name, Cauchy? Is that what it is? Cauchy. Riemann equations. You can write on either one of them or how together they came up with these equations or what are those equations used for. And then 107, and all these should be at Calc Chat. Then 109, any of the odds 109 through 113, you can explore doing those or think about doing them. They should be at Calc Chat. If you want to follow up on that, you can. That's up to you. Then, applied problems. 115 is area. 117 is marginal revenue. That would be as in economics or finance, perhaps, or things like that would benefit from knowing how to do that. 119 is psychology. 121 you can think about doing. 123 is a temperature distribution problem. 125 is the ideal gas law. Well, okay, I'll leave it. 119, I've already said 119, 121. 123 is a temperature distribution problem. 125 is ideal gas law. 127, modeling data. And then 129 is using a function. Define. It's basically a piecewise defined function, filling in the blank of where a function is not defined. Okay. And 131 is similar to 129, different but similar. And there's for further analysis if you want to look at that. Any questions? 13.3. Oh, I forgot to show you how they did example 8. I think it's very similar to what we did. First thing they did was take the first partials, which is exactly, I think, how we did. I can't read the board because of the glare. Then you did 3 of your second partials, L sub xz, zx, zz, and since we weren't using, see, we had xz, zx, xz, zx, zz. So those are all we needed. We didn't need anything with the y in it because they didn't ask for anything with the y in it. Okay? And they just take them and pretend that you know how they got them, okay? But yeah, you can see all those pretty simply. And the f of xz is equal to f of zx, as we suspected, and the f of these three are all equal because they have the same subscripts, they just are in different orders. Okay, and that was the end of the section. But I can't get it to, there we go. All right. All right, let's move on to 13.4. It'll come up one of these days. Well, maybe it will. Doesn't seem to be doing anything right now. Let me try it again. Well, it seems like PowerPoint is frozen. Not liking this cold weather either, huh? Well, what I'll do then is all right. Chapter 13, functions of several variables, and 13.4, well, I should have gone to the current slide. 13.4 is differentials. All right. Now, what we'll do here, hopefully, is understand the concepts of increments and differentials. Very similar to what we've done with ordinary derivatives, okay? We'll extend the concept of differentiability to functions of two independent variables, and we'll use a differential as an approximation. Very similar to what we did with regular derivatives. So let's start with increments and differentials. So let's say we have a function y is equal to f of x. Single variable, single independent variable function. The differential of y was defined as dy is equal to f prime dx, okay? Which to me almost seems like a redundant statement, because if you put this as dy dx, that's equal to f prime. Let's just say these are two notations of the same thing, but written as a differential, that's, while it seems like almost the same thing, it has another sort of slight, vague nuance to it, okay, of a little bit of difference there. Similar terminology is used for functions of two variables. If z is a function of x and y, two independent variables x and y, now we're talking about, and see up here we didn't mention a delta x at all, but now we're saying delta x and delta y are increments of x and y, and the increment of z, delta z, would then be how much z is changing when f is changed from x plus delta x, comma, y plus delta y, minus f of xy, okay? Now, you've made two incremental changes here. You changed x by a little bit and y by a little bit, and that changed z, in a sense, sort of double changed it, okay? Because you could have done one of these at a time, or that one at a time, and then this is doing both at once. And that's what your delta z is. When you've made a little bit of a change to x and a little bit of a change to y at the same time, the difference in your first z, and this new z is that delta z. Okay, that's your increment of z. Now, here's your definition of your total differential then. Z is a function of x and y, two variables, independent variables. Then delta x and delta y are increments of x and increments of y alone, and the differentials of the independent variable, the x and y, are dx is your delta x and dy is your delta y. Now, that is all well and good, but in my mind, this is the limit of that is delta x gets very small. And I kind of don't like saying these are the same thing, but everything they're going to be doing is based on that concept that differential is not infinitesimally small anymore. It's the same thing as that, which is just some delta x and some delta y. So the total differential of the dependent variable z, and this is just dz here, okay? This is just dz because z is a function, is your single dependent variable. So that's how much z has changed. Now, my heart then, if this is delta x and that's delta y, that is your delta z that we were talking about before. I'm not absolutely certain they would agree with that, but it seems like to be consistent that would be it. Well, what is that change of z? It's the partial, or the curly dz by the curly dx, the partial of z with respect to x, times the incremental dx, okay, or delta x, plus the partial of z with respect to y, or curly dz by curly dy, times dy, your increment of y. And that is the same as f sub x of xy dx plus f sub y of xy dy. That's what your dz is, where you've got both the changes happening. Perhaps at the same time or separately, it doesn't matter, but they both have happened before you get your dz. This definition can be extended to functions of three or more variables. So if w was f of x, y, z, and u, okay, then your dx would be your delta x, dy to delta z, delta y, dz to delta z, and du to delta u. Then the total differential of w, which is dw, not partial, but dw, is equal to partial w with respect to x dx, plus partial w with respect to y dy, plus partial w with respect to z dz, plus partial w with respect to u du. Now, this thing right here, if that dz wasn't in front, there was a 0 after it, that would be, because y'all are both in the other class, that would be your exact differential for a differential equation, right? So we're finally now catching up where you've already been in differential equation. Sorry, it's out of order. But when you got four or more variables, they just continue like that, okay? Now, here's example 1. Find the total differential of each of these functions. Now, they're not saying at any particular point, just the total differential. So you tell me, woo, let me get my pen set up. All right, how do I write this? dz is equal to partial of z with respect to x dx plus partial of z with respect to y dy. That seems like it makes a fair amount of sense, right? And this would be, what's the partial of z with respect to x? Okay, a little louder, I couldn't hear.
0 is the first part.
2 sine y.
2 sine y is the first part. Because there is an x in there, and if you take the partial with respect to that x.
Think about the little z there.
Right. Okay. That's the first part.
It's
Minus
6x y squared.
6xy squared. Okay, dx. Okay. Plus
Negative. Wait, no, it's not negative. 2x cosine y minus 6x squared y dy.
dy. You've done it. Find the total differential of the a function. There it is. dz is equal to that. Okay, let's do the b one.
That's all they wanted you to do?
Huh?
That's all they wanted?
That's all they want. The total differential of the a function. That's it. Now let's do the b.
That's
dw.
equals curly dw.
Second.
Curly
Oh, partial. Okay, yeah. Partial of w with respect to x dx plus
partial w with respect to y dy. Partial w with respect to z.
dz. Is that it? I think it is. Yeah. Okay. Now let's plug and chug and see what we get. 2x dx 2y dy plus 2z dz. Now I'm a little dz myself. Okay. And that's your dw. That's your total derivative of the b function. Okay? All right. What I'm going to do, I hope this will be readable. I'm going to erase this part and just leave our final answer. And let's see if we can read it. I'll do the same thing here. I'm guessing they're going to write on top of it, but let's try. Nah. Okay, they wrote the first thing we did quite nicely, and then they gave what it is. 2 sine y minus 6xy squared dx plus 2x cosine y minus 6x squared y dy. Perfect. The b one, let's see if we can read that. 2x dx plus 2y dy plus 2z dz. Yes. Okay. That was example 1. And that's all they gave us under example 1. We're moving next to differentiability. Okay? So that was finding a total derivative. Done. And it's a pretty simple process, so hopefully it won't take too many more of those. Okay, now, differentiability. For a differentiable function given by y is equal to f of x, we're going back to single variable now, you can use the differential dy is equal to f prime, because f was differentiable. You remember they told us that. So there is a f prime dy, f prime of x dx, such that an approximation for small delta x's of the value delta y, and what you do here is delta y is the difference between f of x plus delta x and f of x. In other words, wherever you started with, then change your x a little bit and see what you finished, And that difference in the y is the difference of alpha of x plus delta x and our original alpha of x. When a similar approximation is possible for a function of two variables, two independent variables, the function is said to be differentiable. This is stated explicitly in the following definition. Function f given by z is equal to alpha of x and y, two independent variables, x and y, is differentiable at x0, y0 if the delta z can be written in the form of delta z is equal to f sub x at x0, y0, because that's where it's differentiable, delta x plus f sub y at x0, y0, delta y, plus some epsilon 1, some incremental change, well, actually, in your delta x. So, well, some incremental change epsilon y, epsilon 1 will multiply by delta x, and the incremental epsilon 2 multiplying by your delta y, where both the epsilon 1 and epsilon 2 are approaching 0 as delta x is approaching 0, 0. Okay. And they usually say they're both greater than 0. They say approaching 0. Is that really what they mean, or do they mean greater than 0? Nope. They say approaching 0. Okay. Let's sit down because it's harder to, well, it's hard to read from down here, too. The function f is differentiable in a region R if it's differentiable at each point in that region R, at every x0, y0 in that. Okay. Now that's a lot of blah, blah, blah. It's differentiable there if it can be written in that kind of form. Okay. Show that this function, f of xy equal x squared plus 3y, is differentiable at every point in the plane. Okay? Now to show this, you'd have to take the partial with respect to x and the partial with respect to y. That gives you everything in the plane. Okay? So they say delta z, which I want to call just df. I hope that's going to be okay. Okay? And what would that be?
What's this big thing up top, isn't it?
What's that?
Are you saying that's going to be delta z?
Yeah, that's your delta. If this is indeed z, then that would be your delta z, or dz. Okay? Because they didn't give us a variable, I just called it df, which is whatever that variable is, that's what it is. Okay? Which is delta. You can call it delta f if you want to. And what would it be?
F sub x.
Say again?
It's going to be f sub x.
F sub x
Of x0, y0.
at x0, y0
Times delta x.
times delta x
Plus f sub y at x0, y0. Delta y plus.
No, that's all we got on this one. And what would those things be then? That's your f.
So we got
2x delta x plus 3 delta y. Okay? Now, those are defined everywhere. There's no problem with that, those partials anywhere, so therefore it's differentiable at every point in the plane. Now, that would seem like to be, that would be enough. Okay, but that's not quite what they're saying here. Sorry, I thought they were going to be a little more reasonable with this, but here's what they're saying. They say let z equal the f of xy. Okay? And then they say, if that's true, then delta z, which we were calling that 2, is equal to, and they break it into the things that we did at the very beginning. F of x plus delta x, y plus delta y, I can't read my writing there. Hold on. Okay, that's a plus, that's a plus. All right. Minus f of xy. That's your delta z. Okay? Now, what this tells you to do is f of x plus delta x. Here's your f of x. So write that as f of x plus delta x, y plus delta y. Okay? That would be, your f function says take the x, the first variable, the x, and square it. Well, the first variable here is x plus delta x. So that would be x plus delta x squared, okay, plus 3 times y plus delta y. That's the new variable for x, okay? Okay, and then we'll do minus, this would be x squared minus 3y, because that will be parenthetical. I could have taken another step, I probably should have. So what would this be? X squared I'm sorry. 2x delta x. Okay, good. Okay. I was waiting and my pen was dragging. 2x delta x. One more term there. Delta x squared, right? Right. Okay. Next. 3y. Minus x squared minus 3y. Alright. Here's an x squared minus x squared. That goes to 0. Plus 3y and a minus 3y goes to 0. So this is 2x delta x plus delta x squared plus 3 delta y I didn't need that soon. No, I got it. Okay, yeah. Yeah, that's it. All right, there's your delta z. 2x delta x plus 3 delta y plus x delta, or delta x plus 0 delta y. I left off the 0 delta y, sorry, but fine. All right, now what is that? F sub x, which is what we did up here, delta x plus three delta y, okay, which is what we have. F sub y is 3 delta y, okay, plus, oh, and I left off, okay, I'm sorry. I was writing this as an F term. Okay, that is what it is, but let me write it this way. Man, I just got a cramp in my neck. I don't know why. Okay. This was alpha sub y delta y from up here. Now, notice the next thing it says is epsilon 1. Now, this is from the previous page over here when we were using this terminology here. Alpha sub x, add our x0, y0, alpha y there, delta y. Then you have a E1 delta x, a E2 delta y. Well, there is no E1 delta x plus E2 epsilon 2 delta y. Now, this thing must be, if E1 is equal to delta x, you have that, and if E2 is equal to 0, because there is no other term there, okay, for your delta y. And that's what they show here too. Because certainly this E1 is going to 0 as delta x to 0. That's pretty obvious. And this 2 is already at 0 as delta y is going to 0. So it becomes, I guess, clear to them as your delta x, delta y are going to 0, then the f is differentiable at every point. So we showed it here. They showed it here with all your epsilons and everything else. Okay? Now, again, that's kind of almost seems like a lot of blah, blah, blah in some sense. But says, be sure you see that the term differentiable is used differently for functions of 2 variables than for functions of 1 variable. Okay. Now, for 2 variables to be differentiable, you have to have all these conditions met. For one variable, you only have 1. Here we have basically 4 terms there. So there is a little bit of a difference there. A function of 1 variable is differentiable at a point when its derivative exists at every point. For a function of 2 variables, however, the existence of partial derivatives, alpha sub x and alpha sub y, does not guarantee that the function is differentiable. And we go back, well, over to example 5, which is coming up, and we'll see that. The next theorem gives you a sufficient condition for differentiability. Let's see if they had all this written here. Oh, okay, wait. Let me erase my stuff. Here's what they're doing. Okay, so this is what it said. Show that this function is differentiable at every point in the plane. So let z be that, which is what you said too. And I erased it, but I had it up there. The increment of z at an arbitrary point xy in the plane is that delta z, okay, how much z is changing when f goes from x to x plus delta x and y to x, y plus delta y. And the difference between that and your original f of x, y is your difference in z, the increment in z. Now, so let's see what it's telling you to do. F of x plus delta x y plus delta y would be x plus delta x squared plus 3 times y plus delta y minus x squared plus 3y. Okay. We've done this. We did it exactly like this. Okay. When you expand the binomial x plus delta x squared, you get x squared plus 2x delta x plus delta x squared. Okay, that's the first one. Plus 3y plus 3 delta y minus x squared minus 3y. And then the x squareds go out and the 3y's go out, and you're left with 2x delta x plus delta x squared plus 3 delta y. Okay. Now, what they're wanting you to see now is that this is the partial of f with respect to x, 2x delta x, and the partial of the second part with respect to y, that's the 3 delta y. Okay? And then there's an extra delta x squared here that you don't have up there, but that would just be a 0 times the delta y. This is 2x delta x, 3 delta y, delta x, that's your delta x squared. And then since you didn't have another term for the other delta y, they put a 0 delta y. Okay. Now to get this to match up with what we did on the previous page, that was your L sub x, delta x. This was your L sub y, delta y. This was your epsilon 1 delta x and the epsilon 2 delta y. So the epsilon 1 was your delta x, epsilon 2 was simply 0. Now all you have to show is that this epsilon 1 is going to 0 and epsilon 2 is going to 0. Of course, it's always 0. As your delta x, delta y is going to 0, 0. Well, certainly, as this is going to 0, that is going to 0. As delta y is going to 0, 0 is going to 0. So, yeah, it follows that f is differentiable at every point in the plane. The graph is shown here, and I'm glad they drew it and I didn't have to. Don't let these lines confuse you. They're not part of the graph here. This is some sort of sheet that's turning like this, which they had actually written the function down again for us. It was 2x plus, no, it was x squared, x squared plus 3y. Oops, too far. Okay. X squared plus 3y. The z is equal to that. So when y is equal to 0, you would have z is equal to x squared. So when y is equal to 0, you would have a parabola. I just don't quite see it in this picture. I'm sure it's there. It's behind. This curve is coming out, I think, in front of it. We'll just take your word that is the graph. It looks, it is a terribly weird angle. And the x is here, the y is over there, and the z is up there. you can see begin to see sort of the parabolic nature, the x and z, that's reflected that way, and the y and z is sort of a linear thing, and you get that too. But again, I'm glad they drew it and I didn't have to, because I'm not sure I could have gotten that to shape up anywhere like that. But anyway, here is your sufficient condition for differentiability. If f is a function of x and y, and f sub x and f sub y are continuous in the open region R, then f is differentiable on that R. So that's what's sufficient. They aren't saying anything about necessary, they're just saying sufficient now. If your first derivatives are both continuous in the region R, then f is differentiable on R. Because that's how you define it. It's partial of f with respect to x dx, partial of f with respect to y dy. Okay. Now, this is the beginning of page 906. Actually, we're at the end of time, aren't we? Almost there, aren't we? Yeah.
2 minutes.
Huh?
2 minutes.
2 minutes. So I don't think we'll be able to get very far here. We'll begin with approximation by differentials, which are they're sort of okay. I mean, they just seem like almost much ado about not much, okay? But anyway, in 13.4, I think you can do any of the odds 3 through 7. They're all at Calc Chat. 3's at Calc View. 9 through 13, they're all at Calc Chat. 11's at Calc View. 15 and or 17, they're both at Calc Chat. No, okay, hold off there. No, okay, just do 3 through 7, because we'll be using a differential as approximation. That's what we'll be doing next. So just 3 through 7, that's all. Sorry, wish there were more. But you have some from the previous one. This is a very short section, so we'll finish this next time and go on to 13.5, which is the chain rule, which is fun, which I think we've already almost done. And then we'll finally get to directional derivatives and gradients, which is a very practical use of partial derivatives. And then we'll talk about some tangent planes and normal lines. This is a long chapter, okay? And then extrema of functions. We'll do that, just like we did with first derivatives. And then applications of extrema. I'm trying to remember if we actually do that. I think not. I think we'll just do a quick slideshow of that, because it's a really short section. And Lagrange multiplier, same thing. Just a quick slideshow, because we're just running out of time to do this many sections. That's 10 sections in this chapter. That's a bit much. So we'll get, that's quite a few pages left to go. So we'll move on with this. But this, to me, and the next chapter are the most important 2 chapters in Cal 3. Partial derivatives and multiple integration. We'll get to some other things too, but these are the due. And no wonder they're so long, because they do cover a lot of material. All right. I think